All right, we're going to start the final section of Chapter 10, 10.3, percent composition and chemical formulas. Now, percent composition is part over whole. When you think about a percent, you say you got an 85%. That means you got 85 out of 100. By definition, the percent composition is the mass of each element in a compound compared to the entire mass of the compound and multiplied by 100%. There are two ways to do percent composition, and we're going to do both. The first is calculating percent composition when using the given formula. The three steps in doing it given the formula is: first, you must calculate the molar mass of the compound. Then calculate the mass of each element in the compound. And third, the mass of each element divided by the mass of the compound times 100. And the example we're going to use is water. Percent composition of water is the total mass of hydrogen over the total mass of water to get the percent hydrogen. So in the calculation of 18.0 grams of H2O, 2.0 grams are that of hydrogen. So 2 divided by 18 is 11%. The percent composition of oxygen would be the total mass of oxygen divided by the total mass of water. In this case, 16.0 grams oxygen would be 1 mole of oxygen, and the overall molar mass is 18. So 16 divided by 18 times 100 is 89%. Now you'll notice when you finish, your total percent should add up to a sum of 100, and 81 plus 11 does that. Now, more likely, you would not be calculating the molar mass, or I should say the percent composition, using just a formula. You would use data from an experiment. So if you are doing it this way, first thing is we measure the mass of the sample. Then the sample is chemically separated or decomposed. Third step is the masses of the components are determined. So if it's separated or decomposed, you then get the mass of each of those pieces. And the percent composition is the mass of each one of those elements divided by the mass of the sample times 100. For example, find the percent composition of a compound that contains 2.30 grams of sodium, 1.60 grams of oxygen, and 0.100 grams of hydrogen in an original 4-gram sample of the compound. So to get the percent composition, we want the percent. What we're going to do is take each one of those parts, 2.3, 1.6, and 0.1, and divide it by the total, which is 4. So the percent sodium is 2.30 grams divided by 4 times 100 gives me 57.5%. The grams of oxygen, 1.6 divided by 4 times 100 is 40.0 grams of oxygen. And 0.1 grams of hydrogen divided by 4 times 100 is 2.5%. Now to check it at the end, 57.5 plus 40 is 97.5, plus 2.5 equals 100. When you are doing these, you should get your percent within 1 decimal place above or below 100. Now here's a little different problem. This time we're given the percent composition and the mass of the sample, and we want to figure out how much each of the species, the carbon, the hydrogen, fluorine in this problem, make up of that 0.562 grams. So this is going to be basically just using a little algebra to rearrange the formula. So we know that percent is equal to the mass of the component over the mass of the compound times 100. But we're already given those. Those are our 3 H's underneath the grams of sample. So then you're going to take each one of those percents times the mass of the sample. So here I will show you. It's just rearrangement by algebra. So here we go. I've got 0.562 grams. I multiply that by 13%. That gives me 0.0371 grams. I have 0.562 grams times 2.2% is 0.0124 grams. And the 0.562 times 84% fluorine comes out to 0.477. Now, to check your work, what you're going to do is add them together. Because we know 13 plus 2.2 plus 84.8 is 100%. 0.0731 plus 0.0124 plus 0.477 equals 0.5625. Now, if you look at your original mass, it's 0.562, but always remember, the last digit being estimated can be plus or minus 1. Now, percent by composition worksheet. This is very similar to what we just did in that final problem. We're given the chemical composition of sucrose by mass. It's 42.20% carbon, 6.50% hydrogen, and 51.30 oxygen. And we know that the mass percent is the mass of the element over the mass of the compound. So number 1 says, suppose you analyze the composition of an unnamed compound and it shows that you have 51.30% oxygen, 42.2% carbon, and 6.5% hydrogen by mass. What can you conclude about the problem or about the compound? It must be sucrose because it has the exact same setup and the exact same percentages. 2. What is the mass of carbon in 5 grams of sucrose, 50 grams of sucrose, and 500 grams of sucrose? Well, percentages are easy in the fact that they are doing per 100. So no matter what the mass of the sample is, it's going to always be 42.20%. That's in 5 grams, 50 grams, 500 grams. It does not change. Percent composition does not change no matter the mass of the sample. How many grams of oxygen are in 50.00 grams of sucrose? Show your work. Well, this one is very similar to the problem we had just done. So I'm going to take my 0.00 grams of sucrose and I'm going to multiply it by the percent oxygen of 51.30 and I get 25.7 grams of oxygen. That is equal to 51.3% of 50. How many grams of carbon are in 100 grams of sucrose? Now this one's a little bit easier because if you realize what percentage is per 100. So if I have 100 grams and it's 42.20%, then I'm going to have 42.20 grams. How many grams of hydrogen are in 6 grams of sucrose? Show your work. Well, I'm going to take my 6 grams of sucrose times 6.50% and I get 0.39 grams of hydrogen. A 20-gram sample of ordinary table salt contains 12.13 grams of chlorine and 7.87 grams of sodium. Calculate the mass percentage of each element in salt. So this time we're given the parts and the whole, but we're not given the formula. We're given the breakdown and the mass of the sample. So I'm going to take each of the masses of the elements divided by the mass of the sample times 100. So the first one is 12.13 grams of chlorine divided by 20 grams of sodium chloride times 100 gives me 60.65% chlorine. I have 7.8 grams of sodium divided by the 20 grams of sample times 100 comes out to 39.35%. And as always, if you add those together, they will equal 100%. The last thing we're going to do in this chapter is called determining an empirical formula. All ionic compounds, as listed with their proper formula, are empirical formulas, meaning they're in the lowest mole ratio. Now, I call this the opposite of percent composition. An empirical formula gives the simplest whole number ratio. So this is how we're going to calculate and determine an empirical formula. So if you're given percents, we could do the percent of a sample, but this time we're going to use those percents and assume we have 100 grams of the compound, which then makes the mass in grams equal to the number to the percent if it's not in grams. Then the ratio of atoms in the formula to the ratio of moles in a mole of the compound. Subscripts indicate the number of moles of atoms in a compound. So H2O tells me I have 2 moles of hydrogen, 1 mole of oxygen. Then we have to convert the mass of each of the elements to moles and divide all moles by the smallest mole value and then round to the nearest number. Now I know that's a lot of steps, so I'm just going to walk you through. we have a sample that has 2.128 grams of chlorine, 1.203 grams of calcium. So I want the empirical formula. So what I'm going to do is I'm going to take my 2.128 grams of chlorine and I'm going to multiply that by 1 mole of chlorine over 35.5 grams. That gives me 0.05994 moles of chlorine. Then I'm going to take my 1.20 grams of calcium times 1 mole over 40.1 grams of calcium, which gives me 0.03000 moles of calcium. 0.03 is less than 0.05, so I'm going to divide both of them by the lesser number. So when I do 0.05994 divided by 0.03, I get 2. When I do 0.03 divided by itself, I get 1. So the formula is CaCl2, because remember, when we're doing empirical formulas for ionic compounds, the metal ion always comes first. You could also check it. Once you get the formula, if you can name it properly, then you probably have the right formula. Now, we're going to do another one. This time we're going to determine the empirical formula of a compound containing 7.3 grams of sodium, 5.08 grams of sulfur, and 7.62 grams of oxygen. So I'm going to do the same thing as I did in number 15. I'm going to take the mass of each times 1 mole over the molar mass, get the moles of each, find out which one's the least, and then divide them all by that so I can get whole numbers. So here it is. 7.3 grams of sodium times 1 mole of sodium divided by 23.0 grams gives me 0.317 moles of sodium. 5.08 grams of sulfur times 1 mole over 32.1 grams gives me 0.158 moles of sulfur. 7.62 grams of oxygen times 1 mole over 16 gives me 0.476 moles of oxygen. The least number of those three is 0.158. So they're all going to get divided by 0.158. And when I do that, I end up with 2 moles of sodium, 1 mole of sulfur, 3 moles of oxygen. So the formula will be Na2SO3, which is sodium sulfite. Thank you.